You may be wondering why I've decided to emphasize general exponential and logarithmic functions. In an earlier video, I had actually discussed what the derivative of an exponential function was and talked exclusively how, through your training in AP Calculus, if you are have some calculus knowledge as you're watching this video, you might have just been informed that the derivative of e to the x is e to the x, and that the derivative of the natural log is insert function here. You're going to find out soon enough in this video, but that doesn't really tell you what happens when x changes, right? So what about e to the x squared? Or what about e to the 1 over x, right? So as soon as we change that initial exponent, things kind of go crazy. So we're going to start with, let's start with just this idea. Let's say we were tasked with deriving y equals 2 to the x. Okay, something we have yet to come across in our exploration of derivatives. We can't use the power rule here because the power rule says that the exponent must be a numerical value, and here it is a variable. So if you think back to your time in pre-calculus, and even Algebra 2, depending on where you went to school, if we take the natural log of both sides, this allows us to remove the exponent and place it aside whatever the base expression is. Now what happens next is going to be covered on my implicit differentiation video, so it's okay if you get a little wonked out. If you watch that video, things should clear up, but at this point we can now derive. Okay? So if I wanted to derive the right side, right, I have a constant and a variable. So I can essentially remove this and just derive x by itself. But the derivative of x is just 1, so I don't really need it. If you decided to do the product rule, the same thing would unfold, because when you go to take the derivative of this for that second expression, it's 0, so that second expression would dissipate. Now, this is the first time we've come to a situation where we don't just have, y or f of x on the opposite side of an equation. So, if it were just y, right, we would write y prime, right, the derivative of the function, okay? We're still going to do that, right? We're still taking the derivative of the function. However, the derivative of the natural log is really 1 over whatever our input is, okay? And we would just simply need to isolate this expression. So if I multiply by y on both sides, the derivative of that function, right, so dy dx is equivalent to y. Well, y is really 2 to the x, so it's equivalent to 2 to the x times the natural log of 2. And like I said, this piece here should be a little uncomfortable. This is something we call implicit differentiation that will be covered in my next video, so you might want to go ahead real quick, watch that video, come back. You should be able to process this a little bit more comfortably. But let's now write down the derivative of a general exponential function. So I'm actually going to change this altogether. I'm going to call this, instead of x, right? So the derivative of this function, right? The b represents a numerical base. G of x could represent x, it could represent x squared. Sine of x, I mean, you could have 2 to the e to the x is equivalent to the natural log of the base times the original function itself. for b greater than 0. Okay. Now I want to emphasize this is not the same thing as this. Okay. Here, b represents a numerical value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. Okay. This operates a little differently, and I'll remind you if you have forgotten. So if we wanted to take the derivative of e to the g of x, that would be e to the g of x times g prime of x. So as you can see, slightly different. Now, when it comes to the natural logarithm, that was also something we had taken for granted. So let's define that as well. Yeah, we can do it as that. Actually, the derivative of the natural log ln of g of x. Right? Why do I write g of x and not just x? Because x in itself is a function, and oftentimes, and probably at this point when you're watching this video, you're like mind blown. You're like, my calc teacher never told me that, right? They normally don't. It's not their fault. It's kind of how the AP test is structured. But we want to get away from this idea of just like x and understand or be cognizant that x is actually a function, right? And I'll verify in one quick moment, right? So I'm actually let me verify now, right? So we know that the natural log of x is 1 over x. Well, the input went to the denominator. How did this become that? You derived it. The derivative of x is 1. So the derivative of the natural log, the general natural log, is going to be the derivative of the input in the numerator divided by whatever the input is. So let's say we had something such as derive this. Okay? There's two ways we can do it. I prefer slow and steady wins the race. I'm not a fan of this like memorization thing. So I'm going to set f of x equal to 5 to the x squared, and I'm going to take the natural log of both sides. Okay. When I go to take the derivative of this, right, the natural log of a function, right, I get f prime of x times 1 over f of x, because the derivative of this is 1. Now over here, once again, scalar multiple, so natural log of 5 times the derivative of this, 2x, and then I would simply need to bring the function itself over. So the function itself is this, 5 to the x squared. And that, my friends, is the derivative of the function. A little uncomfortable, a little intimidating, but once again, I really do strongly believe that if we take the long, drawn-out, methodical process, we'll have a much solid grasp of how to derive exponential. And let's just take a look at a logarithmic function. If you decide to memorize the rules, you're doing that on your own accord, and it is not advised, but hey, I can't stop you. Natural log of x squared. And if we wanted to derive this, we have a classic example of the chain rule, right? Because we have an inner and an outer function, so we take the 2, we keep the inside function, subtract 1 from that, so that becomes a 1, times the derivative of this. The derivative of natural log of x would be the derivative of the inside, which is 1, divided by x. Thus, our final form of our derivative would be 2 times the natural log of x, all divided by x. Now, had we made this x squared, this now turns into 2x, this turns into x squared, right? We have to start making some adjustments, right? This would become a 4, natural log of x squared, x divided by x squared is still going to yield us an x in the denominator, that much will change, right? But things that you definitely want to consider, because like I said before, it's understandable if someone just told you previously that the derivative of e of x is e of the x, the derivative of natural log of x is 1 over x, but those old habits die real hard. So I strongly encourage you to sit down and map out this more thought out methodical process. It should lead to a much higher success rate in your future derivative endeavors.